All right, welcome back. This screencast will discuss theoretical yield and percentage yield. And this down here is the formula you use to calculate the percentage yield if you know the actual yield and the theoretical yield. All right, so what is the theoretical yield? Well, the theoretical yield is the potential amount of product that can be made based on reactant amounts if everything goes perfectly or if everything goes according to plan. But of course, this isn't reality that things go exactly as you predict. There are always, in real life and in real reaction mixtures, some factors that can cause us to get less yield than we might otherwise predict in the perfect world scenario. So what are some of those factors? Why do we never usually achieve the theoretical yield? Or another way to put that would be, why do we usually not achieve 100% yield like we might predict in calculations? Well, first of all, some reagents or some reactants, they don't physically hit each other during a reaction. So one thing that we'll see down the road, and I've alluded to it a couple times already, is that we have this concept of collisions needing to happen between molecules if those molecules are going to react. So sometimes there's just the physical reality that molecules don't randomly run into each other like we hope they would in order to react. Secondly, maybe there isn't enough of what we call the activation energy. Maybe there's not enough energy involved in the collision to overcome the activation energy and make that reaction happen. The concept of activation energy is something we'll come back to in energetics as well, but it's the idea that there needs to be like a startup energy. There basically needs to be a spark to start a fire is a great example for it. So, for example, you might realize that wood is fuel, or wax is fuel. Okay, these are hydrocarbons basically that we know have the capacity to burn. So why is it then that every time wood is in contact with oxygen, it doesn't spontaneously burn and turn into CO2 and H2O? Well, of course, that's because there's a certain activation energy that needs to be overcome for that wood to oxidize and burn. And that's why we always need to light a fire with a spark or a match or some sort of ignition, right? For example. So maybe there's not enough activation energy. And then thirdly, maybe there's an alternative pathway or process that might occur to create a byproduct. So maybe during the reaction, we can have little side reactions happening based on some of the products produced or some of the conditions or some other things we didn't realize are also in the reaction vessel or that the reaction is exposed to. Basically, little unpredicted chemistries can also occur to draw down our yield of our desired product. Okay, so let's go back to this example from the limiting reagent video. And if you haven't watched that limiting reagent video, that's the one you should watch first here. So we left off with this example that we actually solved, and the solution is here in a part of it. So when 35 grams of CS2, so there's your CS2, and 17 grams, 17.5 grams of oxygen, there's your oxygen, are mixed, we predicted that 23.5 grams of SO2, there's the SO2, would be produced, okay? We did this using the limiting reagent calculation. So if you go watch that limiting reagent calculation video, you'll see that's how we figured this out. This value of SO2 right here is therefore what we would call the theoretical yield. Theoretical yield. It's like the perfect world scenario. That's how much of it we would get. We could never get more than that, but we could always potentially get less than that. And in practice, we almost always do get less than that. So the question here, that we're really trying to answer here is if only 19 grams of SO2 is produced, what was the percent yield? So we'll have to use the percent yield equation here, the actual yield, which is this bit here. What kind of colors do I have left? Blue. So this would be what we call the actual yield. That's what we actually obtained in the reaction in real life. We'll divide that by the theoretical yield, times it by 100, and we'll be determining the percent yield. So let's do that. Let's pump that in. We actually got 19 grams. We predicted we would get 23.5 grams. And so when we punch it into our calculator, we get something like 80.9%. Okay? So the percent yield in this process was 80.9%. Now, it's important to note here, I don't know if I mentioned it anywhere else, so let me just mention it now. We use the grams directly, the mass, in the percent yield equation. You could also use moles in this equation if that's what you have. It doesn't really matter. You can use moles or mass, and that's because they're interchangeable based on the same factor, which is the molar mass, right? So you can use moles here if that's what you have, if that's what's available. Okay, so use either. All right, here's one we can take on, and it gives us an equation here. CO, which is carbon monoxide, that's this guy right here, plus 2 H2s, some hydrogen gas. I don't know why there's no state symbols on there, probably because the guy who wrote this forgot to put them in, but that would be gas as well. Ugh. Come on, pen. That would be gas. And then it's going to produce, well, this is actually methanol, so maybe that would be a liquid, maybe that would be a gas. We don't know. It depends on the temperature, okay? So if we have 500 grams of, if 500 grams of carbon monoxide reacts in excess hydrogen, 485 grams of CH3OH methanol is produced. What is the percentage yield? So if we're going to figure out the percentage yield, let's work backwards and see what we have to do to process this, all right? So this is the question. What's the percentage yield? We know the percent yield is going to equal whatever the actual yield is over the theoretical yield times 100, right? So we know the actual yield. That's this number right here. I'm just going to highlight this. That's the actual yield because they told us that's what is literally produced. That's what is produced, okay? So that's our actual yield right here. The theoretical yield, we don't really know what that is. We're going to have to determine what this is, okay? So we have to determine the theoretical yield. To determine the theoretical yield, the question basically is how much product is produced. And to know how much product is produced, we have to use the limiting reagent. So you can pause the video for a second and ask yourself, which one of these reagents is the limiting reagent? All right, if you looked at this, you would see that they tell us in the question we have excess H2, so we have plenty of this, as much of this as we want. It means we have extra, we have a surplus of H2. That means that the limiting reagent in this case is actually carbon monoxide, okay? So this is our limiting reagent. It tells us that in the question ultimately, all right? So we're gonna use the limiting reagent to determine the theoretical yield of product. Remember, it's the limiting reagent that controls how much product is made. So we're gonna use that to determine, let's call it the theoretical yield this time. The theoretical yield. Okay? All right, so what are we gonna do? We're gonna compare a mole ratio. Remember that the stoichiometric coefficients, the 1, 2, and 1 in this case, that is a ratio of moles. Well, we don't have moles, we have mass, right? So we first have to convert that into mass, into moles. So what's the moles of CO? Well, you know, we use mass over molar mass. The mass we have is 500 grams. The molar mass of carbon monoxide, if you go digging around on the periodic table, is 28.01 or 28.0, depending on what periodic table you have. I think the ones in the IB data book show 28.01 because carbon's 12.01. Pump that in, you're going to get the moles are equal to 17.85 roughly if you have 4 significant figures. Okay, so that's how many moles of that. Then we can say, well, if we're trying to figure out the moles of C3OH that are going to be produced, then that's going to be the 17.85 moles of carbon monoxide, and the factor is 1 to 1. I'm going to write it out anyways, but you can be like, yeah, it's the same. Why is he writing so much? Just to show you that the units work and to get you in the habit of doing the right thing, man. There we go. Cross those out, and you're going to get 17.85 moles of your desired product, obviously. So this is one way to express the theoretical yield. Okay, so we've got it there in moles. The issue is we've got our actual yield here. Remember the one I labeled blue. We've got our actual yield in mass, in grams. So we have to then take that extra step and convert that number of moles of methanol into mass, into grams of methanol. So let's do that. So the mass of methanol, sometimes you need a lot of paper for this stuff. So they hopefully give you lots of space to answer. The mass of methanol is going to be equal to the number of moles times the molar mass. So 17.85 moles times, what's the molar mass here? Again, refer to the periodic table. Get poking around. It's 32.05 according to my calculations. And so the total final mass of it is 572.2 grams, roughly, somewhere thereabouts, okay? So that is actually our theoretical yield, okay? That's that number. Okay, so we know our theoretical yield. That's if everything went perfectly, that is the mass of methanol that would be produced. Of course, the question clearly says we didn't get that much. Surprise, surprise, what we actually got was the 485. So to determine percent yield, we're going to pump in 485 divided by 572, and we're going to times it by 100. Bada bing, bada boom. What do we get? We get about 84.8 or 84.76, or somewhere thereabouts. That's our percent yield. Okay, here's one that is going to be measurably difficult than the others. There's a few steps here we'll have to sort out, so let's read it carefully and figure out what we need to do. So this one, we've got methanol. I think I called that exact same molecule ethanol in the previous example, so pardon me on that one. Stand corrected. That's methanol, and it's reacting with carbon monoxide, and it's producing ethanoic acid. Okay, so what mass of methanol is needed to react with excess carbon monoxide to make 5.0 times 10 to the 5.0 times 10 to the 3 grams of ethanoic acid if the expected yield is 88%. Okay, so let's write down what we do know. First of all, we know in this reaction that we have excess carbon monoxide, so that one's going to be in excess, and more importantly, that means that the methanol over here is going to be the limiting reagent. Okay, so this is the one that we're ultimately trying to figure out how much of that we need to put in, because it's going to control the product. We also, for the first time, see this term, the expected yield. Now that's basically saying the percent yield is going to be 88%. So let's use the percent yield formula first of all, and make sure we know what we're trying to figure out here. And maybe you've already figured out that we're looking to determine the theoretical yield. because we're given the actual yield, or like it's as if we're a chemical engineer and our boss is telling us like we have to make this exact amount, and we know the efficiency of this reaction, or we know what the percent yield of this reaction is, so we better plan to make that exact amount. Okay, let's see if you can sort this out. So we're going to take the actual over the theoretical, and let's just work with that. We know that the percent yield is 88%. Let's write it like this, and we could rearrange it. So let's rearrange and say what we really need to solve for is the theoretical yield. So if we rearrange this whole thing, we're going to get that the theoretical yield is equal to the actual over the percent yield. Okay, we need the actual yield. Let's just convert this right now. Did I say 500? It needs to be 5,000. The actual yield needs to be 5,000 grams or 5 kilograms, and we know that the percent yield is 0.88, which means that we need to plan for a theoretical yield of 5,700 grams. Okay, so that's going to be our theoretical yield. So let's work with that. So again, we're dealing with, if we have that as the target theoretical yield, what mass of methanol do we need to like react to get that? Well, when we're trying to relate this certain product back to this reagent, the only basis of comparison has to be moles. So we have to convert this to moles. All right. So let's do that. I'm just gonna clean up the screen from my view for a second, and let's convert this thing to moles. So we need to know moles of ethanoic acid. That's going to be this mass that we just determined there, divided by the molar mass. I should maybe write that equation out for you first. Mass divided by molar mass. Mass is 5,700 grams. Molar mass is, if you look at the periodic table and total it all up, dip, 60.04. Then that equals 94.9 moles, which is a lot, but this is industrial. We're chemical engineers trying to meet a quota here. Okay, so we have 94.9 moles is how much we would need to plan to produce. How much of the methanol is that going to be? Well, we need to then use the molar ratio. So the moles of methanol, what's the ratio? Well, first, did we even check that the thing is balanced? Oh my lord, let's check that it's balanced. If you count the carbons and you count the oxygens and yada yada, you're going to see that yes, it is balanced. Whoops, throwing this thing all over the map. Yes, it is balanced. Okay, so the moles of CH3OH are equal to the moles of CH3COOH, which means that the moles of methanol are also equal to 94.9. All right. So we're done, right? Not quite, because it asks us what's the mass. So we have to convert that to mass now. Of course, we need the molar mass of methanol to do that conversion. So the mass of methanol is going to be equal to the moles times the molar mass. So 94.9 moles times molar mass from the periodic table will be 32.05. That sounds familiar because we used it last time also. And punch that into your calculator, you get 3,032 grams. Now, that's cool. We can get the answer right with that. But you might want to notice that actually you were only given 2 significant figures in the question. So we could probably reduce this to 2 significant figures by writing it the way they gave it to us, 3.0 times 10 to the 3 grams. Okay, so that's what mass we would need to put in to produce this theoretical mass of 5,700, knowing that we're not going to get the full 5,700. We're going to get what the boss is asking us to produce, which is 5,000 grams, 5 kilograms. Hopefully you found this helpful.